As I said, basically the midterm is the first 5 weeks of what we've done, and we'll go through the major concepts of what we talked about. The first week we talked about the history of recording. We talked about the progression of the recording industry and recording arts from the late 1800s till now. Obviously, it went from, the first sound recording was actually a needle scratching in some soot on a slide, just to capture the motion of what the airwave looked like visually. Right? That was the first capture of a recording. Incidentally, using computers now, they read those slides and they were able to get like a 1.5 second recording from Alexander Graham Bell, reproduced in audio. But they haven't been able to play it until we had a computer to read the scratches in the soot to recreate what that meant. And Alexander Graham Bell experimented with different organs so that he could figure out how our hearing worked, and made the first device to try to capture sound using a human cadaver ear, which I think is kind of eerie. It's something that I always remember. So he used a human ear from a dead person to try to figure out how to make a device that would capture sound. And then we went through the whole history briefly and how recordings were used, and not just for musical purposes, but initially for stenographers, so that people could dictate and then somebody could translate later and type out a letter. It was used to entertain troops during the Second World War. They'd send recordings back and forth. Nowadays, they just have a reporter on site anywhere in the world, and it's just Wi-Fi'd up to a satellite and comes to us live. But back then, they could just send photographs, and they could send movies, which were, 8mm movies, and then they could also send sound recordings. So it took about 2 weeks to get the news back here when they were sending it from Europe. So that's the first thing. So then it ends up that I go through a whole history, which basically there's one card, I don't have it pulled up now, but it gives sort of the history and timeline of different recording devices, starting with phonograph tapes, and obviously analog was before digital, so tape machines were before digital recordings. The digital recorders, started out with the ADAT, or the DAT player, which was a 2-track digital machine, then the ADAT, which was 8-track, and then the Sony digital tape machines, which were multi-track, 24 and 48, and then eventually it all developed into Pro Tools, which was a computer-based, software-based recording. So we also, after that, we talked about the basic properties of sound, because if we're going to record sound and manipulate sound, we should know something about it. Right? If we have distance and amplitude on an axis, and the sound wave looks something represented like this, we talked about the fact that this distance was lambda, or wavelength. It's a dead giveaway when I say wavelength, because it's a wave and it's a length of one cycle. It's an actual length of how long it is. Talked about 3 basic types of sounds: periodic, impulse, and noise. We're mostly talking about periodic. An impulse is just one strike, and then it travels through time and it's gone, like a snare hit. And then periodic has a period, a periodic wave like a sine wave. Noise is just basically just all noise. Has no period, has no time to it. An impulse looks like this in time. An amplitude looks like this, and it moves in time. Periodic wave, even in time or distance, either one. So we talked about this being the amplitude, this being the wavelength, and that there's a simple relationship between the speed of sound, which we did say in the first class, speed of sound is important. And it's important mostly because it tells us that sound takes time to travel a distance. And it travels much slower than light. Light is almost instantaneous. You flip on the light switch, light goes on, it's almost instantaneous. Of course, we know that it is not. It takes years for light to get from a star to us. So it's very fast, though. So in our real world on Earth, it's almost instantaneous. Where sound is much slower. About 1130 feet per second. So I could actually literally stand a second away from you in terms of the speed of sound and scream at you, and it would take a second for my voice to get to you. Okay, so the speed of sound is so important because it relates the wavelength with the speed and the frequency. What is frequency of a sound, of a wave, of repeating periodic sound, periodic wave? Is the frequency is how often it cycles. This is considered one cycle from beginning to end, and then it starts repeating itself. What was the other one? Frequency is defined as the speed of sound over lambda over the wavelength. So they're intimately related. So the frequency is related to the length of the wave. The speed of sound relates them. Okay, so that's one reason the speed of sound is important. Let's continue. The distance between the beginning and the end of a cycle is called the wavelength. And we did discuss that low frequencies are very long. 40 cycles is like 28 feet long. And like 2 kilohertz, which is, where your voice has diction in it, those frequencies are very small, right? So they go from very long to very small. And that leads us to the conclusion that long wavelengths or low frequencies need a lot of energy to produce them because it has to move a lot of air a lot of distance. And that's actually really, I mentioned a good way to remember it is why is it that you only hear low frequencies coming out of a room when the walls are closed and the doors are closed is because low frequencies have more energy and can actually get through the wall so that you can hear it. High frequencies don't have as much energy, so they can't get through the wall. That said, low frequencies have high energy, and low frequencies have long wavelengths. And as you change the frequency, say you double the frequency, the wavelength gets shorter. You can picture in your mind what happens if you double the frequency. It means the wavelength gets shorter. You make the wavelength longer, the frequency gets lower. Just this relationship's important to remember. So we talked about 3 different types of sound waves, and we're dealing mostly with periodic. We talked about how sound travels, right? We talked about how sound is not a wave like up and down like a water wave. It's more a longitudinal wave, so it travels on an axis, the x-axis pretty much. And it moves by compressing air molecules and then rarefaction of air molecules. So it's kind of like a spring moving through the air rather than a water wave. We talked about some of the uses. Remember, we talked about some of the uses of sound, how John Philip Sousa was against sound recording, and he's a very famous guy who composed all these marches. In the early 1900s, he was against recording of sound because most people felt that music was to be played by musicians as a one-time performance that people could observe. And still, to this day, I have bands come into the studio and go, no, we all want to play together to capture the magic. And then, of course, they all play together, and it's not very magical. And then they overdub and replace things and fix everything. So very few times have I recorded like a whole band at once and kept everything intact, because it was just so amazing we couldn't get any better. So the technique of recording today has gotten to the point where the band will come in and play together to capture the vibe, and then start replacing and fixing all the different elements, except perhaps the drums, because the drums have been played to the vocalist and the other musicians, so his feel was complemented by the other musicians that he was hearing in his headphones. And then if that's a good drum take, then you can rebuild on that and keep sort of his feeling, but perfect all the other parts where you didn't play so good, like the guitar player was a little out of rhythm or the vocalist was singing a little flat. We talked about hearing a little bit, right? That was in the 3rd week. So the 2nd week was more about properties of sound, and we talked about resonant frequencies, that an enclosed room, or you can think of it like this, where you blow into a bottle and you get a tone based upon how much airspace is in the bottle. That's the resonant frequency of the bottle, because you excite a frequency to reinforce itself bouncing back and forth. In this room, I think I made the example that if I was speaking and sound was hitting one wall and bouncing off the other parallel wall, there would be certain frequencies where that distance would be half the length of the frequency, and therefore it would bounce off the other wall and reinforce itself. Or one full wavelength, or a wavelength and a half. All of these are overtones that are reinforced, all frequencies that are reinforced in a room. And there's many different modal sources for resonances in a room. For example, parallel walls, parallel floors and ceilings, the walls going around like a diamond, like a billiard ball would, around the 4 bumpers. That's a mode. It's called a tangential mode. And then there's the oblique mode, which is off the wall, off the ceiling, off the wall, off the floor, off the ceiling, and so on, all the way around. Like you wrap a ribbon around a gift box from one corner to the opposite corner. That would be called an oblique mode. Now, these modes aren't exactly super important to remember. Actually, I was actually just mentioning them because I wanted to impress upon you how many different modes can be excited in a room, and that then can be taken to how instruments work, acoustic instruments. An acoustic guitar, the shape of it, the size of it, has a certain resonance. That's why small guitars sound different than large acoustic guitars. That's why violins sound different than violas, different than cellos or basses, right? And the larger the instrument, the lower the frequencies it can resonate at because of the size of the instrument, and the enclosure can reinforce lower frequencies, and that's why a bass, stand-up bass, is so much bigger than a violin. And they can't even play the same notes down there. But the viola and the violin can probably play some of the same notes, but they sound different.